Today our speaker is Sante. I would like to thank him for coming to this one. It's a good pleasure.
Thank you for inviting me to speak here. It's a pleasure to visit Bolivia. I think that's the pronunciation for the first time. There was a bit of fog today. I hope I will be able to see the mountain later on. Today I will talk about the work that has been done in the field of cosmological perturbation in the framework of F1 gravity. This is the work that we largely done in collaboration with the University of Cape Town. I was a postdoc there and the dance. So here's the outline. I will briefly talk about problem of dark energy, which is one of the motivations about introduce of gravity. Then I will introduce the main tool that I use to obtain the Cosmological approach. And with that, I will construct a theory of covariant gauge environment perturbation for gravity. Then I'll just give you some information on how to find the ground dynamics and the ground and the theory of perturbation. Essentially, I'll be ready to give you some general results on gravity. And I'll apply that to a simple example, and I'll give you some conclusions. So, the evidence for dark energy is nowadays there is more dark energy on Earth than we imagined. It's one you can see in the picture. Source of evidence come from different kind of sources. Essentially only three ways in which you can interpret dark energy. So the first one is the statement of ignorance in terms of macro-energy content of the universe. So you mentioned there are some other fields which we have not discovered in Earth different fields. This is the first explanation, for dark energy. Attempt to understand dark energy this way. There are other more complicated models, dark energies, quantum fields, high essence, quantum fields, and others. The second line of attack that one can have regards the actual geometrical structure of space-time. So we all the time we do cosmology, we assume that the universe is correctly described by three properties of Walker metric, which is homogeneous and isotropic. But it's also true that this metric emerges from a small-scale structure which is non-homogeneous and isotropic. And the way in which we can match the small anisotropic and homogeneous structure units to the large-scale homogeneous isotropic is highly non-trivial. And in fact, there is a lot of research that is going on this, on the field of averaging, but also on the analysis of the understanding of dark energy can be explained by the fact that we are not exactly in purely homogeneous isotropic. The third heavy, which is the one that we'll consider here, is that the dark phenomenology, and here I refer explicitly to dark energy, but dark matter is no different, it is then connected to the fact that low gravitation is not what is Einstein told us, at least on large scale. This is kind of more relevant better, but also, I guess, also the most challenging. So let me just restrict the discussion to the model that will be analyzing today, which is essentially a F-bar graph. For F-bar graph, there are two reason essentials why these models are interesting for that. And on one hand, we know that this kind of theories naturally make cosmological solutions which are characterized by accelerated expansion, which this doesn't happen, which doesn't happen in general relativity. And on the other hand, we know that these theories are recovered as low energy limit to something more fundamental. So if you believe in string theory, supergravity, and all these very general conditions, you know that the low energy limit, none of them produces essentially an incentive to general relativity. So even if for some reason F-bar gravity has been commented lately in the past few years, some issues which are resolved, instabilities and so on, is still, structural this theory is still something that comes down from these more general schemes. So it's a problem that has to be addressed. These are the two main reasons why we like to investigate these kind of theories. But however, when we actually try to make calculations, what we realize very quickly is that these theories have a high degree of linearity and has structural difference in terms of the theoretical setting with general relativity. And this means that classical methods that we use for general relativity to analyze the cosmology, physical properties, are not always the best method we can have or we can choose. So there is a need in research of gravity and other theories of gravity to devise methods of investigation. So here the discussion becomes a little bit technical, so I'll give you a work line of what I'm going to do. I'm going to introduce the CMA-UBI method, which are the one plus three covariant equation. I'm going to give then a choice of a convenient frame, this will be clear later on. I'll then explain to you what the linearization is like in the frame of the 1 plus 3 approach. Then I'll introduce the background, define some perturbation variables, and give perturbation equations. Okay, so let's start with the 1 plus 3 covariant approach. Some considerations. The 1 plus 3 covariant approach is what can be thought as a semi-tetratic formalism. In tetratic formalism, we choose 4 legs of the turbine, and then we split everything according to this leg of the turbine. Here, we just choose one leg, essentially finite flow, which is in cosmology associated with some physical flow, flow of the galaxy clusters in cosmology. And we leave the rest of the degrees of field basically untouched. They organize in surfaces, which are orthogonal to this finite flow. On these surfaces, we can define some specific objects, geometrical and thermodynamical. So there is physical interpolation, as you will see, as far as you consider, of course, school. The most interesting aspects of the covariant approach, that the Einstein equations, so the additional field equation, only enter in the way in which space-time and matter interact with each other. And this means that when you have a modified period of gravity or an extension of gravitation, the only change will happen in the way in which matter and space-time interact. So it's very easy for us to generalize this kind of the other great advantage is that differently from standard perturbation theory, you can use the same formula from the same variables to analyze at the same time background and perturbations. And this makes things easier when you want to actually introduce measurements and so on. So let me just start constructing the 1 plus 3 equations. As I said, I need to set up a kind of flow. I'll leave it general because this is the covariant aspect of the field. So I will just assume that this vector is a timeline, and then I will construct a projection tensor. This projection tensor will be the metric for the orthogonal surfaces. And then what I do, I define 2 different variables, which are essentially projection of the covariance along the line of flow and orthogonal to the line of flow. I also introduce a 3-point form, which will reduce to integrals and so on. Then what I do, I look at the kinematics for the flow. So I take the quantum reduced flow and I decompose it in a reducible way. And this allows me to define my kinematical quantities. So I'll have a quantity for deviation from geodesic motion, the quantity that describes the expansion of the geodesic flow, shearing of the geodesic flow, and the rotation of the geodesic flow. There are other variables actually that one can define, which are related to the by tensor, but they are not relevant for scalar perturbations. Yes.
Index A is 4-dimensional.
Say again?
The index A, B, are they 4-dimensional?
They 4-dimensional. Yeah, it's a traditional language for that. But I should have said that. These are all 4-dimensional indexes. So, okay. So this is the kinematics. Yes.
And that tells you that you cannot have the internal.
Yes, it's a special vector, which is the one that moves with matter. But in general, since the formula is completely covariant, I can choose any vector. So I can assume the point of view of any observer, essentially. So I can choose to sit down on a particle of dust and be corrected by expansion, or I can say, okay, I want to move like a special object. And what is nice is that the equation gives you automatically all the effects that are connected with your specific point of view. This is quite interesting, other than, as we will see, very compact. So these are the variables that describe the kinematics of the geodesic flow. Of course, there is the other half of the world, which is dynamics. So given essentially expressed as a tensor, I can also do a decomposition in terms of the vector UA and H. And I can define quantities like it. Isotropic pressure flux, of course, is connected with known adiabatic processes. Isotropic pressure, fluid shearing, and other particular cases of that are related to non-standard fluid, non-perfect fluid density. Okay, so essentially my variable will be the kinematical variables and the thermodynamical variables. Now what I have to do essentially is to include the information that I'm treating at Flow gravity. So for gravity, people that know about it, theories can characterize by the fact that the action for the gravitational interaction is not linear in the Ricci scalar, but in fact is a general function of it. In fact, it does not even need to be fields if one wants to make a real connection with particle physics. The field equations are given by this long expression, and this is the main important, most important feature of them, which is essentially the fourth order part. So here you have the derivative autometric, which are over the four. An important property of the equations for gravity is that you can always recast them in a form that is generally plus some effective fluids, and this makes our work of constructing one plus trigonometric approach much easier. Let's see a bit more the details of these stress energy tensor. There's a first stress energy tensor which is related to the standard matter energy tensor, which would be small MPD. There's only the minimum copy that comes in, and then a second part, which is an effective fluid made essentially by geometry, right? One can do then the decomposition of the fluid that I was telling you before for both of these objects, and also the effective fluid. And for the first one, you get this kind of quantities. So essentially, you just rescale by from right. So if you assume now that, as we will, that the standard matter is a perfect fluid and there is no anisotropic component or strange pressure that come in, essentially these two variables are zero, and you have only to utilize. For the other geometrical stress energy tensor, let me call it curvature fluid, so just even the name tag. What we have is all the quantities. So all the thermodynamic quantities are essentially different from zero. So this might appear strange at first sight, because we know that we can do calculations on a fluid gravity in Figma-Robertson-Walker, right? In Figma-Robertson-Walker, Q and I should be zero, because we only admit perfect fluid. So what is going on? Well, what happened is that these quantities are only dependent on the projected readings. Right? The Friedman-Robertson loop is actually homogeneous. Yes.
Why should the right express with 0 on the 3?
Well, this isotropic pressure is 0.
It doesn't have to be a certain number.
Well, if you want, the point of Friedman is that thermodynamically you need to you can only have adiabatic processes. Right? And adiabatic processes means that your pressure can only have a diagonal component. If you have these kind of things, you will have thermodynamical processes which are not really adiabatic. So this should be
yeah, this is true, but it's not really
So physically, two as one is
actually, I can show you. Well, I can't show you because I don't have the equation here. But if you go and introduce the geometrical structure of the Friedman-Robertson work, so you set to zero shear with TCP acceleration and so on, then you plug all these things in the 1 plus 3 covariant equation. They will show you that this is zero. Now you have to be careful because this isotropic pressure is the covariantly defined isotropic pressure, which is not always the same of other isotropic pressure that are defined in other theories. This is a tensor, right?
So I don't understand. No, okay. If I bring to 0, I just was wondering whether it's obligatory or not. Because I remember from even original margin paper, it doesn't have to be 0. It can be, yes, but it doesn't have to.
Well, I'm not sure how you can characterize completely adiabatic processes if that object.
No, I'm not saying that's the process because there was no data this potential.
Yeah, but Friedman-Robertson only needs these processes, so you can't get out. You can't do, Friedman-Robertson work is very, very fun and very useful in cosmology, but you can actually describe very little. Processes like stars, for example, are completely out of data prediction of Friedman-Robertson work. And processes like stars, we have described.
Maybe we can discuss it.
Sure, maybe I don't understand. Yes, but let me just say for now that this should be 0 Friedman-Robertson work, but then we'll sort it out. The reason why these objects depend only on the projected derivative, right? So if you have isotropy and homogeneity, all these projected derivatives have to be 0, right? Which means in Friedman-Robertson work, these objects are 0. So in Friedman-Robertson Walker, and only in Friedman-Robertson Walker, the curvature fluid is a perfect fluid, right? But if you consider perturbation in Friedman-Robertson Walker or other metrics, you're going to have to consider the objects. And this means that when you consider the curvature fluid will be a perfect fluid only if the geometry is a Friedman-Robertson. So the conclusion here is that one has to be really careful about the way in which you interpret the curvature fluid. Somehow you expect this kind of behavior because this, in fact, is not fluid, this is geometry, right? So pure geometry is not pure Friedman-Robertson Walker, so it's not completely isotropic and homogeneous, then the fluid is not isotropic and vice versa. Okay, of course, all the quantities that we define respond to conservation equations, which are the Yankee identities. You write the Yankee identities with this perfect tensor. You have the standard, you assume the standard conservation law for the normal matter, so that object there in the square is essentially 0, and this translates in our variable in these order long equations. Notice that I chose to ignore the properties of T tilde and B. In fact, you can choose to just give the Yankee identities for the standard matter, and the Yankee identities for the curvature fluid is just redundant system. So these are singular, so it makes sense to do it. Okay, so this equation plus the propagation and constraint equation for the mathematical variables that I don't give you because they're very long, are the 1 plus 3 equation. So we have done the 1 plus 3 equation, now we have to choose a convenient frame. So the basic characteristic of the 1 plus 3 covariant approach is the covariance, right? But the covariance does not mean that in itself is not very predictive, right? In order to actually get physical results, we have to choose a person that actually is observing, or a class of observer that is there. And this corresponds to choosing the actual frame. There are different frames. Particle or matter particle, just look at the universe in that respect. One can choose another frame in which, for example, the influx are zero, right? This is kind of the equivalent of the left frame in accelerator physics, right? Or one can decide to think that the curvature of fluid is a real fluid and try to be moving with it, right? This would be this kind of solution. All these choices are completely equivalent in terms of equations, but they allow to actually set to zero some terms in the equation, so they simplify the equation. What we choose is, yes?
You said it can be a vector fluid, you know that there is a frame in which I and U and Z.
Pi and Q, no. There is a frame in which you can set Q to zero, but pi you will never manage. There is no frame that if pi is different from zero, there is no frame in which you can actually set pi to zero.
Then the question is because you said with the red one can have a vector fluid.
Say again?
With the red one you said we can energy momentum tensor with
Yes.
vector fluid.
Of the matter, yes.
Ultimately.
In this one, right? In here, you are moving with it, but this is still not a perfect fluid.
So
Yeah. So you can. The point is that here you can choose where you want to sit, essentially, right? So here you're moving with that. So your curvature fluid is at rest with you with respect to you that you observe it, and the rest of the universe moves around, right? Or the other way around. So yes.
Fundamental question.
Yes.
Your model of the space-time has some similarity with brain model.
Yes. Is that a question or?
Yes, it's not on.
No,
I see.
not really. I mean, in the brain models, what you have a five-dimensional space-time, and then you have a matter surface that corresponds to our four-dimensional space, if I remember correctly, right?
I asked because I have seen that you told us that you have a 3+1
Yes.
dimension
You can-
space separated from
Yes.
the other part.
In fact, I was getting there. It has been done. So you can actually do a 1+4 formalism, and you can treat brain cosmology like this. This has been done by people Donsby and Buchier. Yeah, 2000, the early 2000s. So you can apply all this formalism to brain cosmology if you're interested in it without any problems. It's exactly the same construction.
The curvature which you are using is defined for the 3+1 dimensions, which you use in your action.
Well, the point is that I'm not actually using a curvature, I'm just decomposing it. So if you consider the curvature of the bulk, right, you can do the same decomposition to the curvature of the bulk. Formally, it makes no difference. So the same quantities that I defined there will be predefined in terms of your bulk plus the brain. The point is that these are 4x4 tensors, 4x4 or 4 vectors. In your case, it will be 5 vectors and so on. But there's absolutely no difference between. In fact, what you can do, you can decide to do a different kind of splitting. Since your time coordinate is inside the brain, if I remember correctly, not in the expert, but then you can choose to select an additional direction. So instead of only having time flow, you can also select the 5th dimensional direction. So you have 2 different vectors, right? And then you decompose everything in terms of the time-like, one space-like, and the rest of the free space. And this allows you to do a calculation. This can be done in a relatively straightforward way. This is because all of this is just geometry. So it is reducible decomposition the same way like you do in electromagnetics. You just decompose stuff in vector tensors, symmetric tensors, asymmetric tensors, and so on.
So when you bang on the X of the dimension, it's fast like really standard.
Okay. So we choose this frame choice for 2 reasons. It's the best defined physically. I'm not really very comfortable with choosing this as a frame because we don't really know what this curvature fluid is. So just to be on the safe side. And also corresponds to our very perturbations because in the end we are modulo the proper motion. We are dragged along by the expansion, right, together with the balance class in which we belong. So This kind of seems to be the most interesting point of view for the perturbations. Okay, so we have chosen our frame. Now I have to tell you about linearization. Well, linearization is a bit different in the context of the 1+3 approach, because since we are in a client setting, we can't just write an object in terms of background plus perturbation, because this creates covariance, as you surely know. So we have to do it in a different way. And the different way is the following. We start with the exact equation, which has that in any space time. Then we will consider a special background, for example, Friedmann-Robertson. So now we know that in Friedmann-Robertson law, the sum of the quantities that you have, like the shear, for example, will be 0, right? So we consider order 1, all these quantities which are 0 in the background. And in the equations, we drop all the terms which are order 2, so they contain 2 objects of order 1. So for example, if you consider the full equation for the propagation equation for the expansion, which is essentially the Carloni equation, you find that in Friedmann-Robertson Walker, objects like the acceleration, the vorticity of the shear are essentially 0, so they are order 1, which means that all these terms are order 2. So the linearized version of the Carloni equation would be this one for us. Once you've done this operation on the 1+3 equations, you start to get to something that is manageable. So I can actually show you the complete set of 1+3 equations. This is the linear kinetic part. So there is an equation for the expansion, one for the shear, one for the vorticity. These are the equations for the components of the Weyl tensor, which we will neglect here. And these are the propagation because there is a time dependence, the time derivative here. This we call constraint equation because there is no time. There is no dot in there. Also, I've highlighted what are the components that come in because of the condition. So you see, if you had a different kind of theory, or even some components, some special fluid brain cosmology, the only thing that would change is this side of the equations. The other side is completely. Of course, we have the middles with the concentration equations. So for the curvature fluid, we have this equation. For the standard matter, we have this. So this will be our background. So on these, we have to build the perturbation theory. But before doing that, the important thing is to set up the background, right? As I said to you before, I can use the 1+3 covariant approach to do background and perturbation. So the equation for the background are essentially one equation that is a constraint, which is the Friedmann equation for the expansion. It's μr, it's a short version of the expression that we did before for the effect of the dynamics of the curvature fluid. Then there's the Carloni equation. There is the conservation law for standard matter and for the curvature fluid, and then the constraint that links R to the derivative of the expansion. These objects contain information on gravity, and we have to find a way to solve these equations to get the ground solution. But these are really very complicated equations to solve, right? So also here we have to be smart. We have to find a direct way to look in and to define our equations. So one way to do this is the dynamical system approach. I will not give you all the details of this because this would require another talk, essentially. What I can tell you is that dynamical system is a method that, by clever definition of variables, allows you to make a connection between phase space analysis and cosmological equations. In particular, what you have is that in phase space, fixed point will be a particular solution, essentially. The stability of the fixed point will be the relation between the particular solution, particular cosmological solution, and the general integral. And then you can infer from the general flow information on how the general integral is going to work. So how do we use the dynamical system approach for our purposes? Essentially, what we do, we take a solution, which is an exact solution in fixed point, that has the characteristic that we like, and we look at perturbation theory in this form. This gives an error with respect to consider as a background general integral, but is an error that can be managed and can be recorded in terms of the final analysis. Okay, so assuming that we can use dynamical system approach or any other technique to get a background solution, then of course we are ready to look at the perturbation variable. So the equations, the 1 plus 3 equations that we derived so far are equations which are the equivalent of general linearized Einstein equation. Right? But now in order to describe perturbation, we want to define some objects that are clearly physically representing the perturbation amount of fluctuation. And these objects are 3 vectors, which are given by these objects. So you can see, for example, this guy. This represents amount of fluctuation. This is essentially the variation over the space-like surface of the energy density, normalized and made dimensionless using the scale factors. Right? So this is more clear than this in terms of perturbation variables you cannot really have. Right? The same happens with this. This is the equation in expansion. So the variation of expansion on the spatial upper surfaces. And the same for this, which is the field direction. There is a constraint to links these two objects. In general relativity, you can use only 2 of them and obtain the classical second order equation that describes how the perturbation works. In fMR gravity, things are a little bit more complicated because we have more degrees of freedom. And so we have to introduce other 2 variables in order to close our system. And these 2 variables are structurally similar to the one we define here. So here we have the amount of fluctuation, here we have the richest state of fluctuation. And here we have the expansion, which is essentially the first derivative of the macro energy density. Here we have the first derivative of the richest state. One does this, then it's possible for us to construct a pair of perturbations that contains all the information we want. In fact, however, if we look carefully at the structure of this vector, we realize very quickly that they contain a lot of information which is not directly related traditionally to linear perturbation. And this can be seen if we again do a splitting. So we take the covariant and projected derivative of, for example, the length of D, and we decompose it in a reducible way in symmetric trace, we realize that the antisymmetric terms will describe vortex kind of structure to form with your matter energy density. This one instead will measure the distortion, so the formation of objects which are not symmetric. And instead, only the trace will give the spherical clumping. Now, in linear perturbation theory, we normally use spherical clumping. We don't deal with vortices or structures which are not symmetric. Which means that the only part that is really important for us at this stage is the trace of all the vectors of that area. So our working variable will be essentially the trace of these objects, which are essentially the divergence over the vectors of the structure. Okay. So now we have our variable, we can look at perturbation situation. So we do a lot of calculations, and you get to this first-order system, which is really big. But if you have seen any perturbation theory for gravity, you find that this is the shortest and most compact set of equations that we have, that I've seen at least in the last few years. So we have 4 differential equations plus 1 constraint, which is the one I was telling you before. So it's a 4th-order system. Essentially, I eliminated here the equation for C because normally we tend to keep the equation for variables for symmetry between these variables and this variable. However, the equation for C is quite interesting physically, and let me show you how physics worked it out. So the equation for C is made of 2 parts. The first part, which is proportional to the speed k. K is the spatial curvature index for Friedmann-Robertson rule. So if you have a Friedmann-Robertson rule parametric, k is 0, which means flat upper surfaces, k plus 1 curved spherical upper surfaces, k minus 1 hyperbolic upper surfaces. And then the second part, which is essentially a Laplacian. But this means that if your background is flat, right, the equation basically becomes this. And if you go to long wavelength, so if you go to large scales, to small wavelengths, which means long wavelengths, which means large scales, essentially this object is 0. So C is conserved. And this means that your 4th-order system becomes a 3rd-order system. And if you're lucky enough, as we will be aware with the example we'll show you in a little bit, you can actually integrate exactly the equations and the solution. Okay, so let's go back to the perturbation equations. This perturbation, this system is of course a system of partial differential equations. So in the tradition of perturbation theory, in order to solve them, we introduce an harmonic decomposition. Again, you cannot use the standard harmonics that you use in general relativity because we want covariant harmonics, because we don't want to break covariance, which means that we have to define harmonics using a Laplace equation in which the operator is the projective here. So for these Q, which are scalar harmonics, that are vector tensor harmonics. First, K is the number, Q dot is equal to 0, and of course, every first order quantity can be described like this. So using this expansion, our system becomes now ordinary differential equations that depend on the parameter. Okay, so
it's Laplace, it was 3-dimensional, 4-dimensional.
That would be 4-dimensional projected. So the vector is still a 4-vector, but it's contracted with the projected tensor. So it's got the zero component is 0. I don't know if I have it. Well, so you have your covariant here, right? And this is in fact a 4-vector, so there's 4 slots here, all different from 0. Correct? Instead, this guy is the projection of the covariant equation, and this is level of 0, object, object, object.
And it's covariant.
It is covariant, yes. This is a 4-vector. So instead of bringing the covariance, you actually put set to 0 by that projection tensor the components which you don't like. A nice way of dealing with way which you can set up your perturbation equation is a set of 2 second-order equations. Here, right? I've chosen here the standard mathematical equation and the G-state equation. And this becomes very interesting in terms of the structure. Although I can imagine that the look at it like this looks like a big mess, but we will just dismount the structure equation. I'll show you all the physics that is in there. We're going to start with the coefficients. Okay? So the coefficients are objects which are naturally defined in the background. Right, so they are all 0. So these all objects are all functions of the time on. An interesting way of understanding the physics is to introduce cosmological parameters. You introduce Q, J, snap, omega k, and so on. And you write the equations in terms of this object. This is again very long. You can schematically write these objects in terms of this coefficient. And what turns out is the fact that the evolution of perturbation is very much more sensitive in GR to the feature of the background. So if in GR you have 2 backgrounds which differ only by the parameter snap, this is parameter snap is essentially the 4th order of the scale vector. GR will not see any difference, right? But this equation will, which means that they generate backgrounds in GR, not the general background. So one would expect. So, since the equations depend explicitly on these terms, right, whereas the GR equation do not, right, you have, of course, your perturbation depend on this. This is quite interesting because we know, for example, one of the signatures of non-modified gravity is the fact that J is not exactly 1, right? So this reflects on this kind of considerations. Exactly.
If you have GR,
yes.
another CDM, J can be
That's true, but the consideration is that you know that lambda CDM is the correct observational metric, and you want to know if this lambda CDM means automatically GR or not. So you're doing kind of a backward kind of thing here. So you're saying, I know that the data tell me that this is lambda CDM, I want to know if this is GR or not. Right? And if you find exactly lambda CDM, then of course this can be only GR, and then, well, you have to discuss it. But if you find that this is lambda CDM plus an error, then this error can be modified, right? And the errors can be linked to the value of J. in the sense that if j is exactly 1, in spite of the error, you still have gr. And if j is different from 1, then this error means that you are getting something else. This is the idea of this. So that people did recently, we don't have here size points. Okay, so the other interesting thing is the distribution of the wave number in these equations. In GR, you have only a flat spectrum, right, if you have dust, or at least if you have dust or radiation, for example, a spectrum that has two different regimes, right? Here you have three K terms, and this means that you expect at least 4 different regimes for the perturbations. And this also means that there are some observable differences between the perturbations in a gravity and in GR. We will see exactly how these essentially work. Last but not least, if you look at the differential structure of this equation, and in analogy what I told you before about the way in which the equations can be discussed, the differential structure of this equation resembles the one we looked at in GR. So, for example, if you have a baryon photon system, which would look like this in terms of equations, it will have the same kind of structure, so first derivative, second derivative, first derivative, and the other terms like this. And you can try to compare, and it has also some non-trivial distribution of k. You can compare this with the equations that we have. Of course, in order to do a correct comparison, you can't use the equation early r, the variable early r that I use, but you have to define an equivalent delta, so an equivalent version for the quadratic. So delta r will be essentially s squared r. This is the definition, right? So it's the same structure of delta m, which is like this, and right? So essentially, I'm making the same variable, treating the temperature fluid as if it was a standard fluid. And what happened is that the difference in the K distribution is quite clear, right? So you have that all the coefficients here correspond to K with respect to the current fluid system, which only some of them. So this means what? It means that if we were mistaken and we would consider the temperature fluid, we would have an actual dark energy fluid, we want to force it into being an FOR, we will realize at the level of the spectrum that this is not true, because the theory of the spectrum will be actually different. One can look at the kind of expression of this coefficient, but they're very, very large, so I'd rather do it at the level of the example. And let me go to a simple example, the simplest actually you can get, which is this function r to the n, this is called r to the n gravity. You use the dynamical system approach to find a number of fixed points. Two of them are particularly interesting. This one, which looks like a standard Friedmann solution, and this one, which is a power solution. Both are related to values of n. So the funny thing is that when you consider the phase space, this is a diagrammatic, schematic representation of phase space, the point which is almost Friedmann is unstable. There are values of n for which this happens, which are not too far from 1, which is gr. And also the point C is a dark energy error, so it's accelerated expansion. You can prove that there is an orbital from next.
So Friedman-like is in dust line?
No, Friedmann-like is so the solution there is e to the power 2n over 3, 1 plus r. This is what I call Friedmann. So if n is not too far from 1, right, this is more or less what you could find.
So and then you can see
Yes.
it should be similar to the solution of Friedmann that also working with the equation states, with the constant equation states.
But with a slightly different expansion rate.
This chi no Lagrange, chi of n, no Lagrange, the previous chi.
It's just, I don't quite understand what you're saying, so wait.
In your previous chi. Yes. What is chi? It's a parameter.
Scale? This one? Oh, yeah, it's just the coupling constant. It's just you know, this cannot be the standard 1/16G because the dimensions are not right. So you have to take in account that R looks like 1/length minus 2, right? Which means that that has to be 1/length minus 2 to the power n. That's why I would count this. Okay, so G is this one here. C is another power law that depends on the values of n. Let me call it like this. There are values of n which are close to 1, for which this is these objects f of n is bigger than 1, so we actually have accelerated expansion, which is the energy error, and these objects is almost like free. Right? So essentially, we've seen the transition between something with accelerated expansion to accelerated expansion. Right? What we want to understand is how the perturbation equation work around this point. All right, so we just have to plug numbers here. The background is flat, spatially flat. That's the kind of scale factor that we have, meaning it's like this. So we can write down all the quantities that are there. These are long expressions, but they're just algebra. And we can start looking at substitute this equation and start looking at different regimes. So for example, in long wavelength regime, you remember what I said about the equation to C. So we are at scales which are much bigger than the output scales. So K is very small, and this means that the Laplacian is real 0. Since we have K equals 0, then C dot is equal to 0. So C is conserved, C is a constant, which means that our system is now over the 3 rather than over 4. You can actually draw down the complete equation, which is complicated but manageable. You can solve it exactly. So what you get is that the matter fluctuation work with a solution which has got 4 modes. 2 of them are related to GR. So T minus 1 is the one that we find on the GR. This guy here is the one on GR when n is equal to 1. And then there are these two. This is of course derived in terms of dust, just because we want to get rid of dependence on omega 1. There is no problem in finding the solution for other values of omega. The other 2 modes are given by this horrible expression. 117 should never appear in the theoretical physics, but essentially it's the beauty of linearization. And depends on n. So it's useful to understand the situation to actually plot these modes, so these exponents, in terms of the factor n. What you get is this, right? So each of these, each color, I hope you can see it, each color is a different mode, essentially, right? So what happens is that for specific intervals of n, 0.33, 0.71, and 1.32, we have some oscillatory modes with negative real parts. So there's some damping that is some oscillatory damping. Also, normally the perturbation grow faster than the GR ones, right? There's only a very small interval of n in which the modes grow raise less than the standard to the power of 2 hertz. The most surprising feature is another one. It's the fact that there is always a growing mode, even when your background becomes an accelerated background. This means that within the context of FOR gravity, even if you are in eternal inflation, you can actually collapse structures. And this is a complete game changer in terms of how perturbation, how the material works in this term. So in FOR gravity, you can actually, you don't really care about having a Friedman-like transient because you can actually consider accelerated expansion all the time and still form a linear structure. This was quite surprising. To conclude, let's look at the power spectrum. For people that are not at ease with power spectrum, you can imagine this as a quantity that tells us how the fluctuation of matter depends on the wavelength. and also something that gives you an idea of the amplitude of perturbations. We know that in GR, the power spectrum large scale is constant, but the small scale is normally suppressed depending on the feature of the cosmological fluid, and we know that in the case of dust, the spectrum is completely scalar, so it's completely flat, right? So if you try to define and to derive the perturbation spectrum for the case of Archimedean gravity that I showed you, which you get is this object. So you have flat spectrum at very large scales and very small scales. The spectrum, however, have a different power. So small scales have a lower power for n that is going away from 1, although there is a higher power for n closer to 1, which leads to other results, independent results in literature. And then in the middle, you have some oscillations. Right? Where these oscillations are depends essentially on the theory. This is interesting because this is exactly the three regimes that we were expecting from the standard analysis of the case structure of the perturbation equation. Right? Flat, oscillation, flat. If you look at the case of radiation, here the values of n are taken to make things more visible. You have in fact four regimes, right? So you have the first regime, which is flat, then you have the first change of slope, second change of slope, and then the last slope, which is parallel to the radiation. So here is when the radiation kicks in, here and here is the work of gravity.
So,
Yes.
radiation, you look at same sequence like radiation in GR, that's
No.
not fluid.
What I mean is that the W is 1/3 in this equation, this background, and here it doesn't appear, but we use this background as well. So I'm not saying that T is equal to power of 1/3, I'm saying that matter is a perfect fluid if W equal to the topic factor of 1/3, which is not the same. Let me insist a bit more on the two-fluid analogy. So here are the huge coefficients that I told you about in the general analysis of the perturbation. There are a number of k factors there, and here we can understand why the three regime actually emerges. If you take the limit for k goes to 0, these objects become k independent. If you take the limit k equal infinite, also became independent from k. So essentially you have here the two flat parts of the spectrum, and then you can plot in terms of k the coefficients for delta dot n, delta n, delta dot r, and delta r, and you see that they all peaked at the same value. You can't actually see it, but they all peaked at the same value of k, which means that the maximum influence of FOR gravity will happen at the specific k, which is the k which the oscillations are. Right. So what we are actually seeing here is that there is kind of a very strong indication of where FOR gravity kicks in, and this is at a very specific scale. Before these scales, we have flat spectrum. After this scale, we have flat spectrum, right? So any deviation from the flat spectrum one measure can be compared with this result, and you can actually make the analysis and understand what is going on. I'm getting late. I'm going to run. Sorry. Last slide is the evolution of the power spectrum. You can actually start with the initial condition in which your distribution of structure is completely flat, right? And you can run it in terms of time. And what do you find for a specific k? And what do you find that as time goes, small scale perturbation lose power. So essentially, small scale objects merge into big objects more and more and more. And the oscillations start to essentially fall in. So this is how dynamically the spectrum that we have defined, the derived option. Okay, last slide. Are these results general? So we have done an analysis of the equations. We have looked at an example. We have to ask ourselves if this signature that we have is actually general. Our feeling about this is that the answer is yes. And the reason is that the case structure that should be in the equation is independent from the form of the actual interior gravity. Also, when you look at the coefficients of the two fluid analogy, also in that case the equations are completely general. So the K dependence does not change much when you consider other models like R plus 1 to the n, or to the n exponential, whatever other functions are in the model, and so on. So we expect that this kind of result is general. So effectively there is a signature for gravity in the spectrum of perturbations. However, this is not a theorem, so we have not really proven this. This is just something you can use for intuition. Okay, so the conclusions. I showed you 1 plus 3 covariant theory, cosmological perturbations. In case of orthogonal gravity, particular to gravity. In case of Archimedean gravity, I define the behavior of scalar perturbations in a treatment of sloping background. Our results indicate some important difference in the dynamics of perturbations and possible characteristic signature for these theories, which are actually measurable. The moment you find deviation from flat spectrum, you can actually compare these with this calculation, these results, and you can say the reason for gravity that is actually consistent with it. And there are some open questions, however, that need to be addressed. For example, the oscillation of the perturbation at large scales, and above all, the growth of perturbation. Thank you.
Thank you, sir. Another question, please.
So how far can it be related to a scalar, being a conformal transformation,
Yes.
both at the background and perturbation?
Well, and that's a problem that you have. You know, when you do the conformal. Well, finish your question, then I'll
As background, yes. At the perturbation.
Not even for the background. Conformal transformation are very powerful tools, but you have to be careful with it. Conformal invariance only happens when you have vacuum. When you have matter, like in the case we're considering, what happens is that matter behaves in a way which is non-geodesic, right? So when you translate this in the theory of perturbations, since your matter is non-geodesic, what happens is that your choice of frame becomes non-geodesic, and this means that your perturbation will appear different. So the fact that you have this relation does not mean that you can translate from conformal frame results. If you have some specific formula that you need to do, then you can find a formula in the conformal frame and then translate it in the original frame. But the question is that you have to be careful because no physical conclusion that you find in one frame can be straightforwardly taken to the other. So you have to be. Right. So I'm expecting that if you do these calculations in the conformal frame, you will not find this. But that's because the conformal frame is a different universe, not because there is something, you know, that we didn't see in this.
Any further questions?
Can this approach, can we find an easy way to generalize this approach? What you would
It depends on what you mean by quantization.
The quantization of the perturbations now
In inflation, in the context of inflation, or
for example.
In principle, yes. In principle, yes. The problem with the perturbations at that level is that you rely on averages. And covariant averages are not that straightforward. I'm not aware of anybody that has done this so far. But this is a relatively new formalism. No, it's not. Well, 20 years more or less. But it's not very much used yet. So it might well be that people have not done it because nobody knows about it. I've not seen it around. I will not really be comfortable in telling you how to do it because, to be honest, I don't know much about quantum perturbations in inflation. But if you sit down together and we look at the basic steps, compare with
Any further questions?
Last question. You talked something about the changes in the general relativity and the characteristic of the isotropy present of the space-time. So it includes some breakdown of the Lorentz.
Not as well gravity. There are theories that break down Lorentz symmetry, which are one which is gravity shifts or general shifts, for example, or ether theories. There are also torsion theories, but the problem with breaking the Lorentz invariance is that the moment in which you do that, all the covariant structure falls down. So I'm not entirely sure you can apply this straightforwardly to that. However, normally these theories do not destroy completely the Lorentz group. What they do, they separate it in different parts, and each is consistent in itself. So for example, general Differentials does the separation between time and space, but you still have covariance if you look like this in the space part of the thing, and for transformation that preserve time, right? So if this is the case, then I would guess there is a way in which you can set up things, selecting a certain group of transformations and defining some tensorial objects which are tensor with respect to certain class of transformations that generalizes this, but it's not straightforward.
Yes. You said in FFR you have a characteristic, let's say length, this type of theory, you look at the Scalar set. If you look at the tensor sector, something similar?
The tensor sector is not very different from the standard GR. And the reason, if you think about it, it's quite clear, is that in fact, also from what comes out from conformal transformation, these theories have an additional scalar equation. So this means that the maximum impact of their presence will be in scalar-related kind of objects. We solved the equation for the cosmological gravitational waves, which are essentially tensor perturbations. And what happens is that you have solutions which are basically similar, they're Bessel functions, so they're basically similar to the one that you find in general. There are some signatures in the spectrum, but not as strong as this one. So you can make a comparison, but it's not as clear as this. And the reason is that there is no additional degree of freedom that influences the tensor perturbation so much. There is, what happens is that
the equation are different.
no, the equations are the same, unfortunately. What happens?
There is scale less alpha.
Yes. What changes is that the source, the effective source will be different. But that's only the source, so you don't have the differential structure of the equation is the same. So the solution is just Bessel, of the homogeneous plus something else which takes care of the source. So there's no real difference in terms of this thing, at least on cosmological scale. Then you know, when you look at yeah.
And the equation structure is the same. They are not exactly.
They just scale the same coefficients.
I'm not sure if I have here. No. Okay. I thought I had. If you don't mind me opening another presentation, I'll try to see if I can find the results. You can see also the other.
So in GR usually you have the road, UK applied was C squared and it's multiplied over A UK. That's when we do apply A multiply A to A.
These are, yes, okay. So these are the general equations for the tensor perturbations, right? So you can find the tensor objects are the components of the tensor essentially, plus the shear, right? So if you write them down, you have that pi r in this case is given these objects, there's a little shear, so you get this, right? So what happens is that this part here, right, is only modified for these objects and these objects. But this is equivalent to shifting. Yes, there's a shift in the background, which is given by that term, and there's a source term. Then you can solve. I don't know if I have it.
So what's I meant the equation are different. Another thing is that there is no input, so then I'll.
Yeah, but not as different as they could be as they are in the scalar sector. That's what I'm trying to say. Yes. I don't know what I have. Yeah, so you can solve essentially this, and you can see that here, for example, this is GR, and this is the kind of equal that you have here. So when n becomes much bigger than this will square to the n much bigger than 1, that's the spectrum is a bit different, but it's not really much of a difference. Let me see if I have anything in general.
I think it's amazing that without a change on the
Yeah.
equation of evolution, it's much.
This is the long way around. So there are different regions in the spectrum in which you have different behavior of the modes. So some modes can actually grow in certain special conditions, so there is instability there. In another case, there are some dissipation. The safe region is this one. So I don't know quite prepare for this, but yeah, we can.
If there are no further questions, say something.